So welcome back. We are now finishing week 10. I have no idea what lecture we're in, probably 17 or 18. I don't know. But today we will be working on chapter 22, which is inference about a population proportion. Inference about a population proportion. So let's remind ourselves what we've done so far in terms of inference, which is, the major part of this class. In chapter 16, this is a recap. 16 was an introduction to confidence intervals, and specifically, we did a confidence interval for a population mean. We did a confidence interval for a population mean. And if you recall, it was X bar plus or minus Z star, sigma divided by the square root of n. Of course, that was the formula when we know sigma. X bar plus or minus Z star sigma over the square root of n. Then we went to 17, and 17 was an introduction to hypothesis testing. And we did a hypothesis test. We did a test for the population mean. And then after that, we did 18. And 18 was about conditions for inference in practice. It was more about practical warnings about when to use confidence intervals and hypothesis tests and some stuff like that. But there were no additional formulas, right? So there was nothing new formulaically in chapter 18. 19 was just a review chapter, so nothing was there. And then we did 20 last time, and this was inference about a population mean. So again, we had formulas, confidence interval for a population mean, but this time we did not know sigma, so we did X bar plus or minus T star S over the square root of n, and we talked about that. And we also did, sorry? I cannot hear you. You're breaking up. It's very staticky as you're talking. Okay. Was that just me, or do you guys hear the static as well?
He just seemed very quiet.
Oh, he was quiet? Oh, I heard him, but it was like in the background was
kind of like far away. He sounds a little like far away. I don't know.
Interesting. Did you say T star or Z star for chapter 20? T star, you can see it, right? Does my T look like a Z? T star. And then we also did the matched pair t-test as well. So we did all of that so far. And then we did 21 last time. And 21 was comparing, right? We did 21 last time? Right? Yeah, so 21 was comparing two means. So we did a confidence interval for two means. It was x1 bar minus x2 bar plus or minus, assuming we don't know sigma S1 squared over N1 plus S2 squared plus S2 squared over N2. We did that last time. And we also did, looking back at what we did, we also did a test for two means. So that's all the recap. Everything about means, averages. One average, two averages. Do I know Z? Do I know sigma? Do I not know sigma? It was all about averages. And now we're going to work with proportions. So what we do now in chapter 22 is inferences about a population proportion. Proportions are always percentages. What percent of people believe this? What percent of people do that? What percent of this? What percent of that? Which means our answers are always going to be, or our values that we're looking for are always going to be between 0 and 1, 0% to 100%, 0 to 1. And we are going to do, so now for chapter 22. Now for chapter 22. It's all about proportions. So you have a population, and the population has an unknown proportion P. An unknown proportion P. And then we have a sample from the population. With X successes in N trials, i.e. P hats, which is the sample proportion, is the number of successes divided by the number of trials. P hat is equal to X over N, the number of successes divided by the number of trials. Okay, and we would like to create a confidence interval for P. I don't know what P is, but I want to be able to say I have a 95% confidence that it's between this number and this number, for example. Much like we did with means, right? I want to create a confidence interval. So what is the confidence interval for P? Well, the first thing we got to talk about is the fact that there are two different confidence intervals for P, depending on if it's a large sample or a small sample. So there are two dependent on how large the sample is. So first, the large sample confidence interval. To do the large sample confidence interval, N P hats and N1 minus P hats must both be greater than or equal to 10. The large sample confidence interval, N P hat, this is just the number of successes, and N1 minus P hat, this is the number of failures, must both be greater than or equal to 10. And what is the confidence interval? Well, it's centered at my value, P hat, just like my confidence interval for means is centered at my sample value, plus or minus Z star square root P hat 1 minus P hat over N. Again, not deriving it, just giving it. The large sample confidence interval. So let's do an example to illustrate this in action. I'll go to the back of the chapter. Okay, here we go. Example. Cheating. Students are reluctant to report cheating by other students. A student project put this question to an SRS of 172 undergraduates at a large university. You witnessed two students cheating on a quiz. Do you go to the professor? 19 of the 172 answered yes. Give a 95% confidence interval for the proportion of all undergraduates at this university who would say yes. So first, am I allowed to use the large sample confidence interval here? Yes, you can. Because the number of successes is how much? Well, it's not 10 successes, it's 19 successes. And how many failures are there? How many non-successes? Which are both greater than or equal to 10. So I'm allowed to use the 95% confidence interval. So how am I going to construct it? We'll do it two ways. We'll do it by hand, and then we'll do it on a calculator and see if we get the same result. What is the confidence interval by hand? P hat. What is P hat? What's P hat? 0.95. I don't know. Is it 0.95? Where do you get that from? Could be right. Nah, it's not 0.95. It's 0.11. P hat, don't forget what P hat is. P hat is X over N, number of successes divided by the sample size. I have 19 successes and I have 172 sample size. So 19 over 172, which is 0.11. Plus or minus Z star. What is Z star?
Is it 1.96?
1.96 times the square root of P hat 1 minus P hat over N. So So what do I get as my confidence interval? From where to where? What is my confidence interval? Anyone?
I have a question. So on the left, the right side, would that be, that part would be your larger confidence interval, and then the left side, the 19 divided by 172, that would be your left side of the confidence interval?
The minus, when I do the first number minus the second number, that's the left side. First number plus the second number, that's the right side,
Oh, okay.
right? So the middle is 19 over 172, and I plus or minus this value. If I minus or plus, I get.
Oh, okay.
So yeah, I get 0.06362 and 0.15731. Now, let's do it on a calculator. Where do you think you go on a calculator?
Stat,
Stats,
tests,
tests. Which one?
A,
Hold on, I already cooked it. Say it again, please. Which one?
A,
A is correct. The one proportion Z in, oh, Louis already said it. Yeah, the one proportion Z interval. And go ahead, plug in X, plug it in, plug in our confidence. And what do we get?
You did the same thing.
Same thing. All right, same thing. Which was easier? Doing it by hand or doing it on the calculator?
calculator.
Just by a little bit, right? Just a little bit. Okay. Any questions on that, on the large sample confidence interval?
After stat, what option do we choose?
So is it a test or an interval that we're doing right now?
Interval.
So let's go down to the intervals. And what type of interval is it going to be? One sample or two samples?
One sample.
And is it going to be a Z interval, a T interval, or a proportion interval?
Proportionate.
So it is one prop Z int.
Okay, thank you.
You're welcome. Now, what's the margin of error? In our general confidence interval formula, what's the margin of error?
Z star times standard deviation divided by n.
Excellent. Square root of it.
Right.
Right. So Z star, so the margin of error is a thing that we add or subtract to the p hats. It's a thing that we add or subtract to the middle. All right, we'll call this M for margin of error. In the previous example, this one here that we just did, how do I calculate the margin of error? How do I go ahead in the previous example and calculate? I mean, of course, I could just calculate this number, but suppose all I had was the actual confidence interval. How would I calculate the margin of error if all I had was the actual confidence interval? If my interval was from 1 to 7, what's the margin of error?
6.
6 is not the margin of error. 6 is the range from the left to the right. But the margin of error is from the center to the left or from the center to the right. 3, correct?
So would you would do the largest number, subtracted the smallest number, and then you divide by 2?
Exactly. Largest minus smallest divided by 2. I just did that for this particular problem. And I got 0.0468 approximately. All right, margin of error 0.0468. Do you agree with that in the previous example? Right, notes.
Yes.
Suppose I said, oh, that's too big of a margin of error. I want a smaller margin of error. In fact, you're about to do an experiment. You've chosen a topic, you're going to do an experiment, and you're going to do the calculations, and you're going to get a margin of error. And I say, here's what I want you to do. I want you to pick a sample size so big that the margin of error is no more than, let's say, 0.01 or 0.001. I want that margin of error to be really, really, really small. The question is, what size sample do you need to guarantee that the margin of error is smaller than some given value M? If I tell you what M is, what size sample do you need to guarantee the margin of error is smaller than that value? So who here has an idea, right or wrong, as to how to go ahead and calculate this, figure it out? What's a good first step?
Doesn't making your sample size n bigger make your interval smaller?
Yeah, so the question is, what size sample would I need to guarantee it's a given small size?
Don't you use that formula that's like,
What formula? I gave you a formula?
huh?
What formula did I give you?
Well, it's in my notes. It says Z star times sigma divided by margin of error.
Well, that was the formula that I used when I had a confidence interval for a population mean, but I don't have sigma here. I have a population proportion, but we can follow the same strategy as the last one, which is solve that equation at the top for n. Let's first divide both sides by z star, giving me p hat 1 minus p hat over m over n equals m over z star. What's a good next step to do?
Squared.
Sorry?
Square.
Square both sides. P hat 1 minus p hat over n equals m over z star squared. What's the next good step to do? With my eventual goal to get n by itself, what's a good next step?
Would it be to multiply by 1 over the p times 1 minus p?
That can work, but then I have 1 over n equals. So I'm going to do something a little different. I'm going to flip both fractions. So I get n over p hat 1 minus p hat equals z star over m squared, and now multiply by p hat 1 minus p hat. And that gives me this formula here for the sample size. And there's one really big problem with this formula for the sample size. Because remember what the thing is here, right? What's going on? I'm about to take a sample and I want to know what size sample to use to guarantee that my margin of error is a certain size, no bigger than a certain size. So why is this formula problematic? I just rearranged the formula. I did the math correctly. So why is this formula problematic for determining the appropriate sample size for a margin of error scenario? What's so bad about this formula? No, mathematically, everything's okay. Nothing's wrong mathematically with this. The issue is not mathematical. There's another issue with this, more practical. There's a big issue with this formula, but it's not a mathematical. The math was fine. What is the problem with using this formula to determine the sample size that I should use in order to guarantee a small margin of error?
So everything in the formula is correct. It's not, it has nothing to do with the fact that n is not in the formula. It's like on the outside.
No, we're solving for n. I want n by itself. No inequalities here. The math is fine.
Do we need to know m or do we know m already?
Well, I give you m. I say I want the margin of error to be no bigger than 0.01. You say 95% confidence, fine. Z star is 1.96. No problem. No problem there. No problem with m. Do we know successes and failures? Well, how can we know successes and failures if we haven't taken our sample yet? Anyone? How can we, yeah, the p-hats haven't been found yet since we haven't taken our sample. P-hat is only something that we get once the sample has been taken. So how can we use p-hat to find the sample size before actually taking the sample? And the answer is you can't. We have to replace p-hat with something else. So there's two options. Option one. If you have any prior knowledge of what P might be, go ahead and use it. Go ahead and replace p-hat with that value. And the problem will say, based on a study done 2 years ago where they found P to be this, you're going to come up with the sample size. And it's like, okay, well, if we have a prior study that says P is this, I'm just going to go ahead and use it. Option two. Otherwise, replace p hat with the number 0.5. Option 1, you have any prior knowledge, use it. Option 2, you don't have prior knowledge, just use 0.5. In which case,
Can I take this for half an hour?
in which case, n equals z star squared over 4m squared. Because if p hat is 0.5, 1 minus 0.5 is another 0.5, and then 0.5, which is 1/2 times 1/2 is 1/4. So we just get z star squared over 4m squared. So let's do an example to illustrate this in action. A large city is proposing a school tax levy to provide funds to address deteriorating conditions in several older school buildings. You will contact an SRS of registered voters in the city. So it's going to be an SRS, which is good. Everything needs to be an SRS. You want to estimate the proportion of voters who approve of the levy with 95% confidence and a margin of error no greater than 3%. So the margin of error can be no greater than 3%. M no greater than 0.03. What size sample should you use? What size sample should you use? Well, do we have any prior knowledge in this problem of what P might be from previous studies? No, so we're going to use option 2. What is our Z star?
1.96.
1.96, which we're going to square over 4 times, what's our margin of error?
0.03.
0.03. So we take out our calculator. And we do the math. What do we get for our sample size? Oh, don't forget to square 0.03. We square the margin of error.
I got 274.29.
How many? 274?
274.
All right, check your math. Something's wrong there. And something's definitely wrong there. Oh, not Luis. Luis is correct. Well, Luis is, his number is very close to what my math gives me. But I want to, before I say whether he's right or not, I want to speak about one thing. So 1,006, I mean, I didn't use 1.96. I used 1.959963986, which is more exact. So my number's a little bit off. Yeah, so Luis, hold on a second. So the question is, we get something between 1,067 and 1,068, but it's significantly closer to 1,067. So the question is, do we round down to 1,067? Because you can't ask 0.1 persons. It makes no sense to have a decimal amount of people. Do we round down to 1,067 or do we go up to 1,068? 1,006, we always go up, always up, always. It's not that we're not rounding. We're erring on the side of caution. Bigger samples are never a big deal. An extra person can only make my margin get smaller. But going the other way makes my margin bigger, which means it might not be 0.03. But if I go up and it's bigger, it makes it less than 0.03. I don't care. I want it at 0.03. I'm not going to complain if it's less than 0.03. So my sample size would be 1068. Does that make sense? Questions on that so far? All right. So next question. What if n p hat and n1 minus p hats are not both greater than or equal to 10? Well, then Cynthia, you have a question?
Yeah, it was just the n equals equation.
Yeah.
Is the 4, is it all of it squared? The 4m, all of that is squared, or is
No,
it just the?
just the m, just the m.
Okay. Thank you.
What if n p hat and n times 1 minus p hat are not both greater than or equal to 10? Well, can't use the large sample confidence interval, but if n is greater than or equal to 10, if at least the sample size is greater than or equal to 10, then use the small sample confidence interval. So what's the small sample? Confidence interval. Well, first of all, we know X equals the number of successes. And we know N equals the sample size. And we know P hat is equal to X over N. But for the small sample confidence interval, we do it a little differently. We define this new thing called P twiddle. That's the way we pronounce it, P twiddle, which is X plus 2 over N plus 4. We add 2 to the number of successes, and we add 4 to the sample size. P twiddle equals X plus 2 over N plus 4. And the confidence interval then is P twiddle plus or minus Z star square roots of P twiddle, 1 minus P twiddle over N plus 4. So if it's a small sample, instead of the large sample confidence interval, we change it a little bit. We don't use P hat, successes over failure over sample size, which is, the most obvious, but rather we add 2 to the successes, we add 4 to the number of trials, and we use a slightly different formula. So let's do an example. Cocaine users commonly snort the powder up the nose through a rolled up paper currency bill. Spain has a high rate of cocaine use. So it's not surprising that Euro paper currency in Spain often shows traces of cocaine. Researchers collected 20 Euro bills in Madrid, 17 of which bore traces of cocaine. So we have a 20 size sample, 17 of which bore traces of cocaine. What proportion of all bills in Madrid have traces of cocaine? What proportion of all bills in Madrid contain traces of cocaine. First, am I allowed to use the large sample confidence interval? Yes, no, maybe so.
Can you say that again?
Can I use the large proportion confidence interval? With this data?
No,
Oh, no.
Why not?
because n is greater than 10. Because n is 20. It says here that n, if it's greater than or equal to 10, then you have to use a small sample.
Not have to. I do use it, but I should always first check whether I can use the large sample, which is certainly going to be better. And as Luis says, no, because in order to use the large sample, the number of successes and the number of failures must each be greater than or equal to 10. How many successes do I have in this example?
17.
I don't have 20 successes. Or did you, maybe I misheard you. What did you say?
17.
17, I'm sorry. 17 successes. How many failures do I have?
3.
3. So do I have 10 of each?
No.
No. So I can't use the large sample confidence interval. Well, next best scenario, am I allowed to use a small sample confidence interval? Traces of cocaine. Or Madrid. I'm not sure which side you were talking about. So can I use the small sample confidence interval? Well, when am I allowed to use a small sample confidence interval? If n is greater than or equal to 10. Is n greater than or equal to 10 here?
Yes.
Yes. So I can use the large sample confidence interval, but at least I can use a small sample confidence interval. So what is p twiddle as a fraction first?
It's x plus 2 divided by n plus 4,
And what is x?
17.
So what's the numerator going to be?
19.
19. And what's the denominator going to be?
25.
20.
24.
24. So my p twiddle is 19 over 24. So let's form our confidence interval. We get 19 over 24 plus or minus. The problem says use 95%. So what's my z star going to be?
1.96.
1.96 square root of p twiddle, which is 19 over 24, times 1 minus p twiddle, which is 5 over 24, over n plus 4, which is itself 24. So let's see what we get here. So what do we get?
I did mine on the calculator, but I got
And-
I got 0.69351 and then 1.0065.
Well, let me ask you a question. What did you put into your calculator as your values? What was your X?
I put the 17 and the 20.
But
I
those
put
are,
the 19 and the 24.
that's it.
Yeah. Okay, so I got 0.62919 and 0.95414.
And that's what I got by hand. So if you're going to use the small sample confidence interval in your calculator, make sure not to put in the X and the N, but the X plus 2 and the N plus 4. Those are your real X and N's. Make sense, everyone? Again, I'm not giving you reasons why these formulas are in place. There's no explanation for these because the explanations are the one bad thing about statistics more than any other class is how little you can really give in terms of a deeper explanation for why things are the way they are. Quite often you just say, because that's the way it is, and just go with it. Luckily, the majority of the problems are just going to your calculator, plugging in numbers and not popping our answers and using them. But at the end of the day, unfortunately, I just can't give you more information than just here are the formulas, use them. So that is all we're going to be doing with confidence intervals in this chapter. What I like to do for the remaining part is do the hypothesis tests. On the calculator is what option? Well, it's still a confidence interval for a single proportion. So it's still going to be a one prop Z interval. And that part has not changed. What has changed is X and N. You don't put in the actual X and the actual N. You put in the X plus 2 and you put in the N plus 4. Okay. All right. So now hypothesis tests. Now, hypothesis tests. So the null hypothesis will be that the unknown value of P is equal to some specific value, right? This is the unknown true value. And this is the given specific value. And what are the three possible alternative hypotheses?
Greater than, less than, or not, or just not equal to.
Excellent. Greater than that value, less than that value, not equal to that value. And the pictures for the three cases, if we want to show that it's less than, we want a very small number. If we want to show that it's greater than, we want a very big number. And if we want to show that it's not equal to, I'm happy with a number on either side. And the p-value is the probability of obtaining a value more extreme than the one actually obtained, i.e. Z equals value minus mean over standard error. But remember, because I work under the assumption that the null hypothesis is correct, P0 is the actual mean And the square root of P0, 1 minus P0 over N is the actual standard error. We're working under the assumption that the null hypothesis is correct. So we just want the value or the probability that we are past the value that we actually got, which is Z equals P hat minus P0 over the square root of P0, 1 minus P0 over N. Let's do an example to illustrate this, because at the end of the day, examples are the best illustration of anything. So let's take one from the back.
Professor,
Yes,
in that equation, is it, when you say over n, is the whole bottom thing over n or just the?
no,
is it
that's inside the square root.
Okay,
That whole thing's inside the square root. Okay, this is an interesting one. Do chemists have more girls? Some people think that chemists are more likely than other parents to have female children. The Washington State Department of Health lists the parent's occupation on birth certificates. Over a 10-year period, 555 children were born to chemists. Of these births, 273 were girls. This is all for chemists. During this period, 48.8% of all births in Washington State were girls. Is there evidence that the proportion of girls born to chemists is higher than the statewide proportion? Is there evidence? The proportion of girls born to chemists is greater than the statewide proportion. So first, let's state our hypotheses. What is the null hypothesis? If the thing that we're looking to test is not correct, then what would the proportion for chemists be? What should it be? What's the status quo? What's the assumption? It is correct. What's correct? Maybe, maybe not. What is it correct? I need a mathematical statement here. Right? The null hypothesis and alternative hypotheses are very specific. They're in this form. P is some number, or P is less than, greater than, or not equal to some number. So what is the null hypothesis? If the thing that we're trying to test is not correct, if chemists are not more likely to have more girls than everyone else, then what should be the proportion of girls? 0.488. I mean, everyone else is 0.488. Why wouldn't chemists have be 0.488? Right? Status quo. It should be the same as everyone else. And we're testing to see if what? If P is what? For chemists.
greater than?
Yeah. Is it really greater? That's what we're testing for. Is it really greater? So on my sketch, where on this curve would be the values that I might end up with that would make me want to reject the null hypothesis? Which portion of this curve would I say, yeah, the null hypothesis is not likely to be correct. I'll go with the alternative. It's the right side. It's big values. Because we want to show greater than is correct. So let's calculate our Z. According to this, our test statistic Z is equal to P hat Well, what is p hat in our example? As a fraction, what is p hat in our example?
273 divided by 555.
273 divided by 555 minus the mean under the assumption of the null hypothesis, P0. What is that equal to in our example? .488 divided by the square roots of 0.488, 1 minus 0.488 over n, which is 555. So let's compute our z. 0.488 times 1 minus 0.488 divided by 5, square root 273 divided by 555 minus 0.488 this divided by this. Okay, I got my z. What's your z? .1834. That was nice and quick. And what is the probability of being past 0.1834? .4272. 42.72%. So there's a 42.72% chance of getting the result that we actually got if the null hypothesis, or even something worse, more extreme, if the null hypothesis were true. So what is our conclusion? Do we say, wow, okay, let's reject the null hypothesis? Or do we say, sorry, buddy, not enough info. We can't quite reject it just yet. What is our conclusion? Reject the null, Cynthia claims. Sorry to put her on the spot like that. Do we have any agreement or disagreement with that one?
Professor, can you hear me?
Yes?
How do we know that it's 42.72 instead of 4.27%?
Well, the calculator gave me 0.4272. That's 42.72%. That's what moves two.
Okay,
So what do? I have one vote for reject the null. Do I have anyone who wants to agree or disagree with that? Fail to reject the null. Oh, okay, now we have a fight. Oh, wait, Cynthia might be changing her mind. Do not reject. We do not reject. That's too likely of an outcome. Do not reject the null hypothesis. There's not enough evidence to say that chemists have girls more often than anyone else. Yes.
Do we don't reject because,
It's a pretty big p-value.
yeah, okay, because it's above the 0.05.
0.05 is a standard. Yeah, Cynthia, 0.5 and 0.05. Pretty different numbers, but yes, unless there's a specific cutoff point for the problem, you just take 5%, 0.05 to be your cutoff. This is not even close. Right? So because of that, we do not reject the null hypothesis. So are there any questions on what we did today? Because we just did chapter 22. Oh, let's do it on the calculator just to show that we get the same answer. Where am I going to go on my calculator for this one?
You go to you go to stat and test, but you go to one prop Z test.
Excellent. One prop Z test. Very good. So go ahead and do that. And let's see if we get the same numbers as we did the other way.
I got the same thing on mine.
Same thing, crazy. And so much easier, huh? Let's do another one. I want to do here's another example. The French naturalist Count Buffon, who lived in the 1700s, tossed a coin 4,040 times. He tossed a coin 4,040 times. The result was 2,048 heads. Is there evidence that the coin is not fair? Is there evidence that the coin is not fair? So I want you to think about this. Is there evidence that the coin is not fair? Whenever it asks whether or not there's evidence for something, that always means a hypothesis test. Well, not always. You can always, in theory, do a confidence interval. Maybe we'll do both. Oh my God, how much fun will that be? But if we're going to do a hypothesis test, then we need a null hypothesis and we need an alternative hypothesis.
On the calculator, would you do the one prop Z test or would you do a regular Z test?
For this one?
Yeah.
Well, before we go to the calculator, let's ask ourselves, what is the null and alternative hypotheses here? And that will help us hopefully determine which of the choices is the correct one. So what is a good hypothesis test for this problem? Luis on fire. P equals 0.5, P not equal to 0.5. If it's fair, we're testing to see if it's not fair. What's the status quo that it's fair? And if it's fair, the number of heads should be 50%, or the proportion of heads should be 50%, right? 0.5. If it's not fair, we're not specifying which direction, up, down, it's just not 0.5. So Leanne, now that we see the null and alternative hypotheses, which choice are we going to use? If we go to the calculator, we're not going to do that just yet, but if we did go to the calculator, which choice will we use?
I don't know.
Well, is this a proportion or is this a mean?
Proportion.
The whole chapter's on proportions, right? What percent, right?
Yeah.
So it would be the one prop.
So
Well, hold on. Cynthia's asking where 0.5 came from. Hold on. Sorry, 1 second, please.
that's my question. Anyway.
Cynthia, if the coin is not fair, i.e. if the coin is fair, then what proportion should be heads?
Oh, okay, I get 50%.
50%. Right? So the alternative to our alternative, in other words, the original, is at 0.5. So let's calculate our Z. What is our Z going to be equal to? Where's my Z formula? Oh, it's way back. Oh, there it is. What is my Z going to be equal to?
I got 0.8810.
Hold on, I'm going to do that. Well, oh, you did all the math already. Oh, wow, you guys are way ahead of me. Give me the formula. I haven't done it yet. What's the formula for Z? And before I do it, one second, before I do it, where would I get a result that would make me want to reject the null hypothesis?
Either side.
Either side. Okay, so what's my Z? Or not the answer. 0.881 might be correct. I haven't done the math yet. But tell me how you got there. 2048 over 4040 minus 0.5. So divided by 0.5, 1 minus 0.5 over 4040. So 0.5 times 0.5 over 4040, get that, take the square root of that. 2048 divided by 4040 minus 0.5, get that, divided by, uh-oh, I got an imaginary number. How the hell did that happen? Try this again. 0.5 times 0.5 divided by 4040. And then I take the square root of that number, and then on top, 1248 divided by 4040 minus 0.5, and divide that by that. And yes, we get 0.881. Now, remember what the p-value is. The p-value is the probability of being more extreme than 0.881. If it's more extreme than 0.881, that means where could it be? Where can I be more extreme than 0.881?
The right side?
Well, I can be on the right side. I can be in here and reject, but I can also be in here and reject, correct? So more extreme than 0.881 for a two-sided test means past 0.881 this way and past negative 0.881 that way, or just twice the probability of being past 0.881 on one side. So for a two-sided test, we double the p-value. So if I go to if I go to distribution and I put in lower 0.881 upper infinity, and then I multiply that by 2, that gives me 0.3783. If I go directly to the calculator and have it do a one proportion z-test of 0.5, 2048, 4040 with not equal to, what p-value, oh, I hit the wrong one. What p-value does it give me?
0.37829.
Exactly, the same 0.3783. Because the calculator knows that if it's two-sided, it's going to do it on both sides. It's going to double your p-value. So what is my conclusion with a p-value of 0.3783? What do I do here?
You don't reject?
Do not
Do not.
reject the null hypothesis. In other words, there is not enough evidence to suggest that this coin is not fair. Sound good? Next week, not next week, on Thursday, maybe, I haven't decided yet what I want to do yet. I might, isn't it, it is less than 0.5, but it's not less than 0.05. Never mind. Don't shouldn't stutter when you type. That's weird. But anyways, I might do one more chapter. Next Thursday is Veterans Day. A week from today. So on Tuesday, this coming Tuesday, I might do the next chapter, kind of finish confidence intervals, hypothesis testing. And then the Tuesday after we come back from Veterans Day, just do a day of lots and lots of examples. I pick them at random. So I don't tell you, are they means? Are they populations? I mean, are they proportions? Is it one sample? Is it two samples? Is it a large one? Is it a small one? Make it very much test, similar, whatever the word is that I'm looking for, rather than being specific to one chapter. So you kind of know what to do. You have to decide, is it one sample or is it two samples? Is it a mean or is it a proportion? If it's a mean, do I know sigma or do I not know sigma? If it's a proportion, is it a large sample or is it a small sample? Do I want to do a confidence interval? Do I want to do a hypothesis test? And then once you decide all that, you just take out your calculator, go to the right scenario, put the numbers in, I'll pop your answer, nothing by hand. That's the goal, because on the test, it's all calculator. Sound good? Are there any questions with what we did today?
Nope.
Sounds good. All right, well, in that case, I will see everyone on Tuesday. Have a great weekend, everyone.